All right, here we go. So, do you guys know what poly means? Poly, what does poly mean? Multiple, yeah. And gone just is like shapes or sides, so it's multiple sides, like 3 or more sides. So polygons, we've been studying polygons, it's been a triangle, but a polygon is this. There's a couple more things to add to the definition here, but it's a many-sided figure, that's what poly means. Closed figure, I should say. So a many-sided, I think that was bigger, it's a little bit bigger. So a many-sided closed figure made up of straight line segments that don't intersect. So there's a little bit more to it than maybe we've thought about in the past. So it's a many-sided closed figure made up of straight line segments, so no curves, that don't intersect. So ease out. I know, probably better than the definition here. That's the book definition, but better than the definition is like, what is a polygon, what's not? Just looking at a bunch of pictures and deciding what is and what isn't and why it's not. So, what about A? Is A a polygon?
Yes.
It is. It is. It's a many-sided closed figure made up of straight line segments that don't intersect. So that one's a yes. So A is yes. So A is yes. Not quite all of them. B is yes. C is yes. What's wrong with D? Curved, yeah. So this is a no. And then this one's a no as well because, yeah, these intersect. So the other 3 here are all yeses. Yes, yes, and yes. Those of you who ski or snowboard ought to know what, or even sort of concave. You guys know what concave is? No. Skateboard, if it's concave, goes in a little bit, yeah, it's to help keep the feet on the board. And convex is the opposite of that. But here are the official definitions. Goodness. So convex is, here's the official definition here. Probably you have an idea of what it looks like there. You see it now? Okay. So it's no line that contains a side of the polygon goes through the interior of itself. That's what convex means. Some people just say it's opposite of concave. Concave is not convex, well, we went a different direction on it. But concave means it goes in. It's like, think about a cave, right? You're going into a cave. If you think about a skateboard deck, it might go like this a little bit on top of the deck. It would be concave. So, and convex would be popped out. Sometimes you could think of it as like it's taking, and if you were to take and blow air into a corner of one of these shapes up here, they blow air into a corner, it's like all the sides are popped out versus popped in here. So, like this one right here is convex. Here's why officially. It says, no line that contains a side of the polygon goes through the interior of itself. What's happening with figure A is this line segment, if I were to continue it through, that blue line segment goes right through the inside of the shape. So if you can draw a continuation of the line segments of each of the sides of the polygon, and none of them go through the interior of the shape, then it is convex. That's what that's saying. For example, this one would be that, 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 and that. And notice none of those blue lines goes through the interior. That's the official geometric definition of convex. And then concave is just one that's not convex. That's how they went to a lot of us probably have a better understanding of what concave is, and then would say convex is not concave. So if I were to do the little line segment test on A, what conclusion would I come to? Okay. Yeah, because I don't have to go very far here. This one, oh, as soon as I go to this guy right here, I see that it's going right through the interior of it. So that one is concave. And then this one down here is convex. So first thing is, what's a polygon? It's a many-sided closed figure, no segments intersect, no curves. And then we can classify them as either convex or concave. There's an example of each. And then we can also name polygons. You've probably heard of some of these names, at least first few maybe. Okay. The first one we call, it has three sides. We call it a triangle. Yeah, triangle. Right. We'll write some of these down here. The four-sided one would be a quadrilateral, we call it. Yeah. Square would be a special case of the quadrilateral. It's a quadrilateral, quad meaning four. Read any FBI story, studying government here. Five-sided shape, famous five-sided building, yeah, the Pentagon. So pentagon. And if you do any mechanics here, any work on cars or motorcycles or whatever else, six-sided little nuts or six-sided hexagon. And then we get into one that you may not be as familiar with. Does anybody know what the seven-sided one's called? Yes, it's heptagon. H-E-P-T. Heptagon. In case it comes up. I think this one might come up. That's why I'm listing it here. Heptagon. Eight-sided is good old stop sign. Octagon. And then, you don't really need to know anything beyond the octagon, but I think 9-sided is nonagon, 10-sided is decagon, 12-sided is dodecagon. I think if you know through your octagon, you're probably good. What's that? 10 is decagon. 10 is decagon. 9 is nonagon.
Yeah, 20 is a dodecagon.
I think 12 is a dodecagon. When you get into hedron, you're talking 300. Yeah. But if you know through the 8-sided, you're probably good. All right. So if you have your list at least through the octagon, you should be good. You can just ask me if it goes beyond that, or I'll just say a 10-sided shape or a 12-sided shape. I feel like if you know through octagons,
Is there an 11-sided?
there is. It's an undecagon. There's any of them. I mean, but once you get to a certain number of sides, you can just say it's a 12-gon or a 13-gon or a 14-gon. There's certain ones that we name. But that's it. So naming them. So we've got, what is a polygon, concave versus convex, naming at least the first 8, 3 through 8 there. You've got to have at least 3 sides to be a closed figure to be a polygon, right? And then we haven't talked about the regular versions of these. Okay, regular version of the triangle would be the equilateral triangle. Regular version of the quadrilateral would be the square, stuff like that. So we'll get to that. All right, so here's the equilateral. So equilateral is all sides equal. Right, so equilateral means all sides equal. Equiangular means all angles equal. And if it's both, we call it regular. So the equilateral triangle was a regular triangle, or the square was a regular quadrilateral. And then we can have regular pentagons, regular hexagons, and everything else. The regular ones are nice because all the sides are equal and all the angles are equal. It's kind of hard to draw them beyond the hexagon. It's actually kind of hard to draw an octagon. Hexagon's not bad because there's 3 equal sides on the top and 3 on the bottom. So once you go beyond the hexagon, it starts to get hard to draw these regular polygons. And as you add more sides, they look more and more and more like a circle. Yeah. There's a reason for that. So it says tell if the polygon is equilateral, equiangular, regular, or none. There's only one that is regular here. You see it? Yeah, B. The second one on there, that's the only regular one. So this one is regular. And I only see one that is equilateral and none that is angular. So the equilateral one would be this guy. And the Pac-Man there is none of the above. And then we have a parallelogram in there, but that's not, it's neither, none of those. So these other two are none. Okay, so we're building up. So triangles are the building blocks of all these polygons that we're now going to study. We're going to start rolling out different polygons, starting with quadrilaterals. Quadrilaterals, there are many different ones. You've probably heard of them. Rectangles and squares, obviously. Parallelograms, you've probably heard of a parallelogram. There's also a rhombus. You may have heard of a rhombus before. Also a kite, and then trapezoids. So there are all these different categories of quadrilaterals, and that's what we're studying in this unit. Okay, all these different properties of quadrilaterals is what we'll be studying. Now, the way we think about angles within a quadrilateral is we think about, it goes back to triangles. I said triangles are the building blocks. It's like how many triangles make up a quadrilateral. If you take and, by the way, here's the definition of diagonal. Definition of diagonal here is connects two non-adjacent sides. So if I draw in a diagonal of this equilateral quadrilateral up above here, so I draw in a diagonal here, I have how many triangles? Two. I'm connecting non-adjacent sides, right? It doesn't make sense to connect adjacent sides. The adjacent sides are connected by the sides of the quadrilateral. That's not a diagonal. The diagonal has to skip a vertex. So diagonals will split quadrilaterals into two triangles. Now, what is the sum? What is the sum of the interior angles of one of these triangles here in the last chapter? If I add up all the angles here, here, and here, they would equal. Yeah. And if I add up all the angles here, here, and here, they would equal. And does that cover all the angles inside the quadrilateral? Yes, it covers like these two together and these two together, cover each of those angles and then those on the ends. So what ends up happening is that when I split this into two triangles, I end up with 360 degrees worth of interior angle. Does that make sense? So I have 360 degrees worth of interior angle. And it's called triangulating. Okay, it's breaking into triangles. Not overlapping triangles, okay, but two distinct triangles. And because of the triangle sum theorem, I can say that the sum of all the angles in here is 360. And you can do that with a pentagon and a hexagon. Like a pentagon, you'll find out you can break that into three triangles. And 3 times 180 equals 540 degrees. So a pentagon has 540 degrees as the total sum of all the inside angles. And then if you go to a hexagon, 6 times 180 gets a little bigger. And what happens is that as you keep getting bigger and bigger, you have more and more degree measures of those angles. So we throw a theorem at us here, which I'm going to try and help. I'll show you where it comes from. But if you remember that idea of each triangle equals 180, here's the deal. How many sides does this thing have?
4.
4. So that's 4 sides. How many triangles did I break it into? 2. Now, what if I do a pentagon here? Let's take this pentagon right here, since it's already drawn for us. How many sides does a pentagon have? 5. How many triangles can I break it into? 3. So with 4 sides, I broke it into 2 triangles. We can make a chart if we want. With 5 sides, I broke it into 3 triangles. With 6 sides, I'm going to break it up into 4 triangles. So what's happening here is I can only break these shapes up into the number of triangles that are 2 less than the total number of sides, because I cannot connect the adjacent sides. How many adjacent sides do I have to that vertex with adjacent pieces? 2 of them, right? So I cannot connect the adjacent sides and create a diagonal or create another triangle. So that's where the n minus 2 comes from. It's the 2 little green segments here. They are right here. So we've got 180 times n minus 2. N minus 2 represents the number of triangles you can split the shape into. That's where that little formula comes from. So, you can memorize the formula, or you can just remember to triangulate the figure. If I hand you a decagon, 10 sides, okay, without even drawing, how many triangles will the decagon have inside of it? 8 of them. So you go 8 times 180, and you'll have the sum of the interior angles in the decagon. So that's the idea behind this theorem. Okay. It's always number of triangles times 180, or n minus 2, where n represents the number of sides. And the reason we have n minus 2 is because there are 2 sides that when you draw a line segment from the vertex, it does not create a triangle. It's not a diagonal. So, with that in mind, now things are going to change a little bit. We've set things equal to each other, or we've added them up to equal 180. But this time, we've got a little different story here. A little different story. It says find measure of angle Q and measure of angle R. What's the truth about all the angles in the quadrilateral? They don't equal 180. Yeah, so you add them up to equal 360, and that's it. That's the only change. So it's like 80 plus 70 plus x plus 2x has to equal 180. And if you want to do those combinations, that's a 70. In your head, that would be fine. But I've got 150 plus 3x equals 180. And then 3x equals 30. X equals 10. And so now they said find measure of angle Q and R. So that means Q is 10 degrees and R is 20 degrees. 60, 150. That's not 360. What's going on here? I did, clearly. 3x.
I ended up to 180, not 360.
Yeah. Oh, yeah. Thank you. I know I did. Well, what we can always do is we can swap spots here. You can see how it's certainly easy to explain it up here. So we got 360 here, and then we've subtract 360 or 150 from 360, and that is 210, and we get the correct answer 70. That's the beauty of checking here. Huh? So we've got 70 degrees here, and then this will be 140. And those should add up to 360. So that's your built-in check there. It says find the sum of the interior angles of a heptagon. How would you do that? What's that? Oh, you don't have that picture. Okay, don't draw it. Just know that a heptagon has how many sides? You can try to draw it. It's hard to draw a heptagon. Anything over hexagon is hard. So n equals 7. So we're just going to plug it into the formula this time. So I've got 7 minus 2 times 180, or 5 times 180, and 500, 400 is 900 degrees. So that's just plugging in. Honestly, you're going to remember a quadrilateral has 360, triangle has 180, obviously. Pentagon has 540, hexagon has 720. Like, you'll just know all the ones through 8 at least. You'll know. Heptagon is 900, and octagon I think is like 1080. So you'll be using those a lot. Because when it's regular, what are you going to do? If it says it's regular, I don't know if this is regular or not, but if it says it's regular, you can figure out each individual angle measurement by dividing this by 7, right? Figure out if it's regular. If there's 7 sides, so there's 7 angles. If they add up to 900, divide by 7, you know what each angle is. Okay. The sum of the exterior angles of a polygon, one at each vertex, is always 360. It's always 360. So here's the deal. Let me show you a picture here. If I draw in all these little extensions here, so picture this. If I'm standing right here, facing this direction first, I turn just a little bit through that angle right there, right? And then I turn a little bit more here, I turn a little bit more here, and then here, and then here, and eventually I end up turning one full circle. And it doesn't matter what shape I have here, I'm going to turn one full circle if I take and turn through the same number of degrees that each exterior angle represents. That's always the case. So the sum of all the exterior angles of a polygon is 360. So it says find the measure of an exterior, that's just one, of a regular hexagon. I got to have the word regular in there to do this. But if all the exterior angles add up to 360, what would one of these little congruent angles equal? Yeah, 360 divided by 6 gives me 60 degrees. So that's convenient. And then you can combine that with the fact that we know that each of these is a linear pair. Remember linear pair? So if each of the exterior angles of a regular hexagon is 60, can you tell me what each interior angle is? Like right here. 120. Try to get 120. And then that goes all the way around if it's regular. Couple of theorems, pretty easy to use. The triangulation one, the sum of all the interior angles is always the number of triangles times 180, or n minus 2 times 180. The exterior angles is always 360. And between those two theorems, you'll be able to answer any of the questions. You got to watch for the word regular. Okay? They'll just ask you on there, what's the sum of all the interior angles? And they either have to give you expressions if it's not regular, or tell you it's regular, and then you can figure it out. Okay? But those are the two theorems. Sometimes it's really convenient to find the outer angle first, and then just subtract from 180 to get the inside one. A lot of times that's easier than using the n minus 2 times 180 formula. So it depends. But don't freak out if some of the angles end up being decimals. They are in some cases. I think with the heptagon it is. 900 divided by 7. Know that goes in evenly. It might be a decimal. I could try it. But that's about it. So it's just a little introduction there.